Hello everyone, this is Siddiqur Rahman and welcome to the second lecture of the 8th week. So let's start with the learning objective. By the end of this lecture, you guys will be able to describe about asynchronous or ripple counter. And let's move into the next slide to explore the overall outline of this lecture. This slide represents the overall outline of this lecture, or you can say what kind of topics are gonna covered by this lecture. You may find from this slide, such as first, general overview of this lecture. After that, you may get an idea of asynchronous counter. After that, you may get an idea of the features of asynchronous counters. After that, you may learn how to design 2-bit up ripple counter as well as how to design 2-bit down ripple counter. After that, you may learn some of the advantages of asynchronous counters and some of the disadvantages of asynchronous counters also. And at last, you may learn some of the applications of asynchronous counters. So let's start with the general overview of this lecture. Asynchronous counters are those whose output is free from the clock signal. Because the flip-flops in asynchronous counters are supplied with different clock signals, there may be delay in producing. Sorry, I repeat it again. There may be delay in producing output. The required number of logic gates to design asynchronous counters is very less. So they are simple in design. Another name for asynchronous counters is ripple counters. The number of flip-flops used in the ripple counter depends upon. Sorry, I repeat it again. The number of flip-flops used in a ripple counter depends upon the number of states of counter, such as mod 4, mod 2, etc. The number of output states of counter is called modulus or mode of the counter. The maximum number of states that a counter can have is 2 times n, where small letter n represents the number of flip-flops used in counter. For example, if we have 2 flip-flops, the maximum number of outputs of the counter is 4, which means 2 times 2. So it is called as mod 4 counter or modulus 4 counter. Now, from this slide, we may get an general overview, or you can say get an idea about asynchronous counter. So let's begin. The counters in which the change in transition doesn't depend upon the clock signal input is known as asynchronous counters. In these counters, the first flip-flop is connected to the external clock signal and the rest are clocked by the state outputs, either, or you can say, which is symbolized by Q, and the complement of this output, which is symbolized by Q bar of the previous flip-flop. Now time has come to explore some of the features of asynchronous counters. That's why we need to move into the next slide. There are several, or you can say there are some features of asynchronous counters, such as another name for asynchronous counters, or you can say asynchronous counters is also known as ripple counters. Next one, these are very simple in design. Next one, as its design is simple, they use less number of logic gates to construct an asynchronous counter. Operation of asynchronous counters is very slow compared to synchronous counters. Now we need to learn, or we can learn, or we may learn how to design 2-bit ripple up counter. So let's begin. The logic diagram of a 2-bit ripple up counter is shown on the next slide. The T flip-flop, which is also known as toggle flip-flop, are being used for this design, but we can use the JK flip-flop also with J and K connected permanently to logic 1. External clock is applied to the clock input of first flip-flop, and the complement of the first input output, I repeat again, the complement of the first output of the first flip-flop is applied to the clock input to the next flip-flop, which means second flip-flop. So let's move into the next slide to explore the logic diagram of 2-bit ripple up counter. This slide represents the logic diagram of 2-bit ripple up counter, and in this figure, or if you look at the upper portion of this figure, you may find two JK flip-flops. One is left one, and which is named as first flip-flop, and another one is right flip-flop. Another one is placed on the right side of this figure, which is named as second flip-flop. And both the flip-flops have two inputs as well as two outputs. Inputs are symbolized by J1, K1 for the first flip-flop, and J2 and K2 for the second flip-flop. And the outputs are symbolized by Q1 and the complement of Q1 bar, which is for first flip-flop, and the outputs are symbolized by Q2 and Q2 bar, or complement of Q2, which is for second flip-flop. And another important thing for both the flip-flops is both flip-flops are clock passed. Both flip-flop has special type of input which is symbolized by clocked signal, or which is symbolized by clock signal. And for the second flip-flop, you may notice that from the figure, clock passed is one of the complement output, or you can say the second output of the first flip-flop, which is symbolized by Q1 bar. Well, and both the flip-flops inputs are always activated, or you can say high, or you can say logic 1. And if you guys look at the bottom of this figure, then you may find a clock edge signal, or more specifically positive clock edge signal is applied to the clock. And if you look at the clock pulse signal, then you may find there are 4 cycles: first, second, third and fourth. So that's all for the logic diagram of 2-bit ripple up counter. So let's move into the next slide to explore how and when each of the cycle is applied at the clock signal, and what are gonna found, or what we will gonna found the output section of the flip-flops. So let's move into the next slide. Well, this slide represents the initial condition of 2-bit ripple up counter, which means the value of clock pulse, or the value of clock is 0. If the value of clock is 0, in that case, the first flip-flop as well as the second flip-flop does not, or you can say do not activate it. That's why we got the output section of the both inputs, I repeat it again, the output section of the both flip-flops are 0. That's why we write the value of clock is equals to 0, and the value of Q1 is equals to 0, and also the value of Q2 is equals to 0. So let's move into the next slide to explore another condition. So let's move into the next slide. Well, this slide represents a next condition, which means uh, in this slide you may notice that the value of clock is 1, which means positive, you can say the first cycle is applied, or you can say the first positive clock is applied at the clock, which means the value of clock is 1. That's why the first flip-flop is activated or triggered. In that case, we get the output value is 1. Well, if we complement of this output, then we get 0. Why we need this complement? Because this complement is acted as an input or clock signal for the second flip-flop. That's why we need the complement of this output. Since the second flip-flop is not activated or triggered because of the clock pulsed value or clock signal value, that's why we got in the output 0. And here we found the value of clock is 1 and the value of Q1 is 1 and the value of Q2 is 0. So let's move into the next slide to explore when second positive clock edge is applied at the clock. So let's move into the next slide. This slide represents another condition, which means in this slide, or you can say in this figure, the value of clock is also 1. Why this is also 1? Because in here second positive clock edge is applied at the clock signal. Well, when the value of clock is 1, in that case we found the first flip-flop is activated. Then the value of Q1 is 0, becomes 0. Why becomes 0? Because the previous value of this output is 1. But as we are already mentioned in our overview of 2-bit ripple up counter, that the toggle, or you can say the T flip-flop, are being used for designing this type of counter. That's why the previous state should be toggled for the next step. So in this case we got 0, and if we complement of this value then we get 1. And since the value of Q1 bar is equals to 1, that's why the second flip-flop is activated or triggered. And we found on the second output of for the second sorry, I repeat again, and we found the first output of the second flip-flop is 1. That's why we have written in here the value of clock is equals to 1, then Q1 is equals to 0, and then Q2 is equals to 1. So let's move into the next slide to explore another condition. So this slide represents another condition, which means the value of clock is 1, which actually means third positive clock edge is applied to the, or applied at the clock signal. That's why the value of clock is 1. Since the value of clock is 1, that's why the first flip-flop is activated or triggered. That's why we got the value of the first output of the first flip-flop is 1. But remember one thing, the previous value of the first in output of the first flip-flop is 0. As we have already mentioned in the previous slide, that this flip-flop, the output value is should be toggled in every state from the previous state. That's why we get in here 1, and the complement of this value 1 is 0. Since the complement of this value is 0, that's why the second flip-flop is not activated or triggered. Well, but the value of the first output of the second flip-flop is 1. We have already known from the previous state. But the value of the first output of the second flip-flop is 0, present state. But we do not count 0 because the previous state value is remain same from previous to present. That's why we only count 1 here. That's why if you guys look at the condition, then you may find the value of clock is 1 and the value of q1 is equals to also 1 and the value of q2 is equals to also 1. So let's move into the next slide to explore last condition of this counter. Well, this slide represents the last condition of this type of counter, which means fourth positive clock edge is applied at the clock pulse. That's why the value of clock is 1. Since the value of clock is 1, that's why the first flip-flop is activated or triggered, and we found on the first output value is 0 because the previous state the previous value for the previous state is 1, and as we have already known that every next state the output value is toggled, that's why we got 0 here. And if we complement of this value, then we got 1. And since the complement of this output is 1, that's why the second flip-flop is activated or triggered, and we found the value of first output of the second flip-flop is 0 because the previous state value is 1, and since this second flip-flop is activated or triggered, that's why the value of output is toggled, should be toggled, not is toggled, should be toggled. That's why we got 0 here. And we write, and if you guys look at the condition section, you may find the value of clock is 1, or you can say after 4 positive clock edge, and the value of q1 is equals to 0 and the value of q2 is equals to 0. So let's move into the next slide to explore the truth table, which are gonna construct or consist of the previous couple of slides. So let's move into the next slide. This slide represents the truth table of 2-bit ripple up counter, which has 4 columns. Well, at leftmost column, which has header named clock, after this counter output, which is symbolized by q1 and q2. After this you may find another header which is named as state number, and after this you may find another header which named decimal counter output. And if we look at the clock column, you may find the first condition or first state would be initial condition. In that case, the output of the counter, both the output of the counter are 0, and that's why this state has no number, and for this reason the decimal counter output is 0. And if we look at the second row of the clock column, then you may find the first here a word written first, which is first condition initiated, which means the counter's output value is q1 is equals to 1 and q2 is equals to 0. In here the state number is 1, and as we have already know, if the binary value is 0 1, in that case we can write in decimal 1. That's why we placed 1 on the second row on the decimal counter output. Well, if you look at the third row of the clock column, then you may find second. In this case, the counter outputs would be the value of q1 is equals to 0 and the value of q2 is equals to 1. And for this reason, for this state, we placed a number which is 2. State number is 2, and 1 0. If the binary number is 1 0, in that case, which is equivalent to decimal is 2. Well, if we look at the third, sorry, I repeat it again. If we look at the fourth row of the clock column, in that case we may found at the counter's output the value of q1 is equals to 1, the value of q2 is equals to 1, and in this state for this condition we placed the number of state is 3. One, if the binary number is 1 1, then we can write the equivalent decimal number is 3. And if we look at the if we look at the fifth row of the clock column, then we may find there are the outputs of the counter, both the outputs of the counter are 0. That means, or which means, the counter stops its operation. Sorry, I repeat again, the counter stops its operation, and this states is numbered, or this states is symbolized as number 4. And since the 0 0 if the binary number is 0 0, then the equivalent decimal number is also 0. So that's all for the 2-bit ripple up counter. So let's move into the next slide to explore another type of ripple counter, which is 2-bit ripple down counter design. So let's move into the next slide. Well, this slide represents 2-bit ripple down counter. The logic diagram of a 2-bit ripple down counter is shown on the next slide. The T flip-flop, which is also known as toggle flip-flop, are being used for the design purpose. But we can use the JK flip-flop also, with J and K connected permanently to logic 1. External clock is applied to the clock input of first flip-flop, and first output of the first flip-flop is applied to the clock input of the next flip-flop, which means second flip-flop. So let's move into the next slide to explore the logic diagram of 2-bit ripple down counter. Well, this slide represents the logic diagram of 2-bit ripple down counter. Well, this diagram is also similar as 2-bit ripple up counter. The difference in between two, which is in 2-bit ripple up counter, the second flip-flop is the clock signal of the second flip-flop is actually the complement of the first output of the first flip-flop. But in 2-bit ripple down counter, in here the clock pulsed signal is from the first output of the first flip-flop. So there is nothing there is no other differences in between two type of in between two counter. This is the main difference. So that's all for the logic diagram, and rest of the things are similar as 2-bit ripple up counter. So let's move into the next slide to explore the condition of the different types of conditions of 2-bit ripple down counter. Well, this slide represents the initial condition, which means the value of clock signal is 0, or you can say the value of clock pulse is 0. Since the value of clock is 0, in that case both the flip-flops are not activated. Okay, if both the flip-flops are not activated, in that case we may found on the output section of the both flip-flops, which is q1 is equals to 0 and q2 is equals to 0. So let's move into the next slide to explore another condition. What are gonna found, or what we will gonna found on the output section, if the positive, or you can say the first positive clock edge is applied at the clock. So let's move into the next slide. Well, this slide represents another condition, which is the value of clock is 1, which actually means first positive clock signal, or you can say the first cycle, or you can say the first positive clock edge of the first cycle is applied at the clock. In that case, you may find the value of clock is 1. If the value of clock is 1, in that case the first flip-flop is triggered or you can say the activated. In that case, we may found the value of the first output of the first flip-flop is 1. Why 1? Because in the previous state we got the value of this parameter is 0. Since this type of counter is being used for toggle condition, that's why previous state is 0 and the next state should be toggled, which means in previous we get 0 and now we can get 1. Since the value of Q1 is equals to 1, in that case the second flip-flop is also activated or triggered. Then we may find the value of Q2 is also 1. So we can write the value of clock is equals to 1 and the value of Q1 is equals to 1 and the value of Q2 is equals to also 1. So let's move into the next slide to explore another condition. Well, this slide represents another condition of 2-bit ripple down counter, which means second positive clock edge is applied at the clock pulse, which means the value of clock is 1. If the value of clock is 1, then the first flip-flop is activated or triggered. In that case, the output value should be toggled, which means the previous value of this output is 1. That's why we get the value of output is 0 right now. So since the value of output is 0 right now, that's why the second flip-flop is not triggered or not activated. That's why we found, or we may resume, or we may resume, or we may not resume, or we may assume the previous output of the second flip-flop value for this case, for this condition as well, which means the value of Q2 is equals to remain 1. Okay, since from the previous state. Well, that's why we can write the value of clock is equals to 1, the value of Q1 is equals to 0, and the value of Q2 is equals to 1. So let's move into the next slide to explore another condition. Well, this slide represents another positive clock edge is applied to the clock pulse, which means third positive clock edge is applied to the clock pulse, which actually means the value of clock is 1. In that case, the first flip-flop is activated. Well, and the output value is toggled. That's why we found the value of output is 1, because the previous value is 0. That's why this state is or you can say the present state should be toggled. That's why we get 1. Since the value of Q1 is equals to 1, in that case we may found the second flip-flop is activated or triggered, and the output of the first output of the second flip-flop is also toggled, and we found 0. Now if we look at the condition, then you may found the value of clock is equals to 1, which means after third positive clock is, and the value of Q1 is equals to 1, and the value of Q2 is equals to 0. So let's move into the next slide to explore another condition. This slide represents the last condition of 2-bit ripple down counter, which means fourth positive clock edge is applied at the clock. That's why the value of clock is 1. If the value of clock is 1, in that case the first flip-flop is activated, and we found on the output, and we found the value of output is 0, because the previous value is 1. That's why this in this state the value should be toggled. That's why 1 to 0. And since the value of Q1 is 0, that's why a second flip-flop is not activated or triggered, and we can assume that the previous value of the first output of the second flip-flop resumes same for this state. So let's move into the next slide to explore truth table of 2-bit ripple down counter. Well, This slide represents the truth table of 2-bit triple down counter. Well, this slide, this table has four column, as I have already mentioned, for the 2-bit triple down up counter. And if as most of the things are same, but if we look at the decimal counter output of 2-bit ripple up counter, you may find first row is 0, after that you may find 1, 2, 3, then again 0, which is 1, 2, 3, which is actually an ascending order, which is increment by 1. Okay, that's why we called 2-bit triple up counter 1, 2, 3 in this way. But if you guys look at the decimal counter output column, then you may find first 0, then 3, 2, 1, again 0, which means decrement or descending order, right? 3, 2, 1. Okay, decrease by 1. Well, that's why this type of counter is called 2-bit, or you can say ripple down counter. Rest of the things are same. So that's all for the design mechanism for a 2-bit ripple down counter. So let's move into the next slide to explore some of the advantages of asynchronous counter. Well, there are several advantages of asynchronous counters, such as asynchronous counters can be easily designed by T flip-flop and D flip-flop, or D flip-flop. These are also called as ripple counters. We have already known this thing and are used in low speed circuits. Next, they are used as divide by n counters, which divide the input by n, where n is an integer. Last one, asynchronous counters are also used as truncated counters. These can be used to design any mode number counters, which means even mode, such as mode 4. 4 is even number, right? That's why mode 4. And odd mode, such as mode 3. 3 is odd number. So let's move into the next slide to explore some of the disadvantages of this type of counter. There are several disadvantages of asynchronous counters, such as sometimes extra flip-flop may be required for resynchronization. To count the sequence of truncated counters, mod is not equal to twice n, we need additional feedback logic. While counting large number of bits, the propagation delay of asynchronous counters is very large. Next, for high clock frequencies, counting errors may occur due to propagation delay. Now, time has come to learn some of the application of this type of counter. So let's move into the next slide. Well, there are several applications of asynchronous counters, such as asynchronous counters are used as frequency dividers, as divided by capital N counters. These are used for low power applications and low noise emission. These are used in designing asynchronous decade counter, also used in ring counter and Johnson counter. Asynchronous counters are used in mod n ripple counters. Example such as mod 3, mod 4, mod 8, mod 14, mod 10, etc. In the next lecture, you guys will able to know, or you guys will know about synchronous counters. Well, that's all for this lecture. Thank you guys for your attention. See you guys in the next lecture. Till then, thank you.